first summarize our previous discussion on the various transient response and steady state response measures with respect to a standard second order system. You will recall the standard second order system had this model. This is the open loop or the forward path part, output is y, let me say, the error is E, and here is the reference R, and the closed loop Ys by Rs is equal to omega n squared over s squared plus 2 zeta omega n s plus omega n squared. This is your standard second order system. As far as the transient behavior is concerned, we found that it is given by the response to a step input, and various measures were defined as follows: Tr equal to pi minus cos inverse zeta over omega d. Recall that your omega d is equal to omega n 1 minus zeta squared under the root, where omega d is the damped frequency and omega n is the natural frequency of the system. In addition to Tr, we used the measure Tp, which we defined as pi over omega d. Mp, the peak overshoot, is e to the power of minus pi zeta over 1 minus zeta under this root, and Ts is equal to 4 by zeta omega n. These are the measures of transient performance which we had taken. And if you recall, the steady state performance to a step input gave you 0 steady state error for the standard second order system. However, for a unit ramp input, the value of steady state error obtained was 2 zeta by omega n. Okay? So, please see that the question arises, how do we specify these performance measures, how do they come across, how do they represent the total behavior of a system. You will recall I made a statement that omega n normally you will like to be very high, because as you can see from here, a high omega n leads to better speed of response because it appears in the denominator here. A high omega n means a lower Tp because it is here, and hence lower Tp means the rise time, the system rise will be faster. A high omega n helps you here as well as here. So, it means a high omega n is the requirement if you want to improve both the steady state accuracy and the transient response of the system. However, as we said, as I told you that this omega n is limited by bandwidth considerations, okay, or the considerations of implementation of your control scheme. See this point, because you may require high omega n, and that high omega n you may be able to achieve with a very high value of parameter in a system, let us say an amplifier gain. If high omega n requires a very large amplifier gain, then the implementation of that particular gain will lead you to saturation problems, and hence the value of that omega n cannot be achieved. So, what I want to say is this, that probably the omega n rise is possible by suitable design of the hardware, suitable design of amplifiers, suitable design of filters, so that all those problems which prohibit the use of high omega n could be taken care of at that stage. Two primary considerations for limitations of omega n are the noise considerations and the implementation of design taking high omega n, okay, that may create certain problems. This is one consideration. Once omega n is decided, the other parameters which cuts across all through you see is zeta. As far as standard system is concerned, the personality of a standard system is described by two parameters only, zeta and omega n. So, having talked of omega n, let us see how do you regulate zeta. Please see that, look at this, help me please, what will happen if zeta is reduced. From this expression, it may not be that visible, but it will be, you will be able to recall the overall normalized curves we have obtained. This is, let us say, a typical curve for zeta equal to 0.5, then a curve for zeta equal to 0.3 will look like this, a curve for zeta equal to 1 will look like this, and so on. So, you can just see if you have decided on omega n based on the considerations we have already discussed, then the value of zeta is guided by the following factors. 1, lower the zeta, better is the rise time. Though if I mentioned to you that over the range of zeta we normally take, the change in rise time is not very appreciable, but still this is one of the considerations, that lower the value of zeta, quicker is the response reaching to 100% value, and hence better is the speed of response for lower zeta. Similar is the conclusion for Tp. Well, Tp also for zeta lower will become lower. You can see that this is the value of Tp here, this becomes the value of Tp here. So, again better is the speed of response. Look at the steady state error. The steady state error also helps, this condition is also favorable because lower value of zeta gives you lower steady state error to ramp input. And the question now appears on MP and TS. What are your conclusions on MP and TS, please? On MP, it is very clearly visible that lower the value of zeta, more closer you are to instability, because with lower value of zeta the peak overshoot is increasing, and the peak overshoot is guided by the hardware considerations also. You see, your system may not be able to withstand this much of signal. In that particular case, you limit the peak overshoot, or you limit the peak overshoot by stability considerations also, so that because of any parameter variations, a system with large peak overshoot may not become unstable. This is one point which limits the use of zeta. And what is the other point? Please see, the other point is the settling time. You will recall the settling time curve. It was not that simple, it was not a linear curve or a simple nonlinear curve, it was a complicated curve. Omega n Ts, once omega n is fixed up, omega n Ts is on this axis, and here I take zeta on this axis. You will just remember that this is the fall of the omega n Ts value as zeta is decreased. Then from this point there was a sudden jump, an increase, a jump, an increase, a jump, and so on. This let me not repeat it. You see, this I explained to you that this is the behavior the system has, and this particular value is zeta is 0.68 if you take a 5% tolerance. For 5% tolerance, minimum value of zeta is 0.68, and if you take 2% tolerance, this value of zeta which gives you, not the minimum value of zeta, the value of zeta which gives you minimum normalized settling time is 0.68. For 2% tolerance, zeta is equal to 0.8. Please let me point out an error here. In one of my lectures, this minimum value of zeta I reported 0.76. That value is as reported in the literature. Please see, I have done my own calculations and found that the minimum value of zeta really turns out to be 0.8. You can also do your calculations and verify this fact. So, we will be using this minimum value of zeta, zeta equal to 0.8 for a 2% tolerance band. Now, just see, when zeta decreases, you see your settling time is 0.6. So, it means up to this particular point, if you have reached, the settling time is minimum. Now, you may have a response. For example, you see that you cannot say that it's a good response. Let us say this is a response, rise time is very fast, and take another response. In this particular response, you see, though the rise time in the green curve is larger, but still you may like to go for it because of the merit that its settling time is small. This is the settling time in this particular case. It has settled in this curve, while as far as the red curve is concerned, you find that this is the settling time, because settling time is the time after which the curve does not come out of the band. So, you see that rise time is not the only indication of speed of a system. After all, you will very much like that the system should settle down as quickly as possible to the desired level. So, in this particular case, though the rise time is good, but the settling time is more than the green curve, while in this particular case rise time is poor, but the settling time is small, and hence you see that the conflict between rise time and settling time is to be resolved depending upon the application. So, it depends upon the application. You do not want a sluggish initial response. In that case, you will like to opt for the red curve, and if you want the system to settle down quickly, well, the green curve is the optimum choice. So, what I want to say is that between rise time and settling time, there may be some sort of decision process involved, as is in this particular curve, and that depends upon the specific application under consideration. Coming back to this, at least this is obvious that zeta between 0 and 0.68 should be preferred, or preferably, why this range? Preferably zeta 0.68 or around this region is all right, provided other parameters suffice. Now, if you have to go for lower settling time, go to this side, but at least going to this side does not serve any purpose, because if you go to this side, please see, from 0.68 to 1 or from 0.8 to 1, you are sacrificing both the settling time and the rise time. The system is definitely becoming sluggish. You are neither improving settling time nor the rise time if you go in the range between 0.68 to 1. But if you go in this particular range, you are gaining on rise time, you are gaining on steady state accuracy, but there is an increase in settling time and there is an increase in peak overshoot, and therefore a suitable compromise has to be seen to resolve the conflict, and the requirement of the specific application will come to help us. You see, we cannot resolve it without that. Specific requirements of hardware, specific user requirements will have to be taken into account to see which particular parameter or which particular specification is more important. But this is obvious that between 0 to 0.68 the value should be taken, and this value should be avoided from 0.68 to this side to zeta equal to 1 for a 5% tolerance, from 0.8 to 1 for a 2% tolerance, so that the system does not become sluggish. Okay. So, now I can just conclude this particular point, that what happens in industry, what are the applications, how do they resolve these issues. The applications, general applications I will say, normally take zeta between 0.4 and 0.7, where the user has not given you very specific quantitative information. He says I want a good system, that is all. If he says I want a reasonably good system and he does not specify the goodness quantitatively, in that particular case the designer in his wisdom will like to settle for a peak over for a zeta between 0.4 and 0.7 somewhere, because it really meets the specifications of all the types and gives you a very good compromise. Okay? This is what is the general observation. But if the user says, look, whatever you may do, I want a very highly accurate system, that is the static accuracy is the specific demand of the user. Can you help me? Now, come on, please help me. Initially I told you, if my point has been well taken, please see, I say that if it is a general requirement, if the user has not given you any specific quantitative requirement, maybe 0.7 to 0.4 to 0.7 meets your requirement on the peak overshoot, on the rise time, on the settling time and other factors. So, settle down for some value between this range. Now, there is a user who gives you a design problem and says, look, the static accuracy is the prime requirement, whatever you may do. Can you help me, what value of zeta and omega n is in your mind for this type of application? That static accuracy is the prime requirement. Yes, you will recall, for a standard system, we are talking of standard system, what will happen to the other systems we will see later. Es is equal to 2 zeta by omega n. First of all, you will take care of the hardware design appropriately, so that omega n can be enlarged to meet his requirement. And secondly, you will take a small value of zeta. For some very typical application, the value of zeta as low as 0.1 may also be acceptable. What will happen? Your system will oscillate, but let it oscillate before it settles. When the user says I do not mind that, you should also not mind. So, zeta is equal to 0.1, I know that the transient performance will not be good, but he says I do not mind that, and he says that static accuracy is the prime requirement in that particular case. Let the system oscillate. The only thing is that you will have to be very careful that the parameters of your system do not wander, because if such a high oscillation is there, then there is a risk of system becoming unstable also, and the user naturally does not require that. So, you see the robustness of the system very carefully. If the robustness requirements are satisfied, go for zeta as low as 0.1, so that good static accuracy requirement can be given to the user. Okay? These are the specific applications I said. Fine. There are some applications, for example, a robot is carrying a nut, you see, and it has to put at the proper place, and in between there are certain obstacles, and you really do not want the robot to oscillate. The gripper of the robot, the load it is carrying, that should not oscillate, because it can hit the other points on its path. There is a certain trajectory path. In an industry environment, you cannot give a clear trajectory path to the robot, and you therefore want that the robot gripper should not oscillate, and you can probably afford a little more time for the robot to reach its point. In that particular case, please tell me, what is your design requirement? You can afford more time, but you cannot let the robot oscillate. The rise time, let the rise time also may be more, does not matter. Amplitude should be small, and therefore you will like to settle for zeta equal to 1 is a good compromise. If you meet zeta greater than 1, you see what is the use, you see. After all, 1 to whatever may be the application, if zeta equal to 1 you have taken, and because of parameter misadjustments, there is a little 1 to 2% overshoot in the actual system, that probably the user will not mind. So, zeta equal to 1 seems to be a reasonable design, because it is a good compromise between the requirement that you do not want an oscillation and the requirement that the settling time should be small. These two requirements, if you have to meet, probably a good compromise is zeta equal to 1. So, that way this is also a very specific application. So, I want to conclude my discussion on this point, that will for specific applications very specific design will come up, but for otherwise we will be mostly concerned for the values of zeta between 0.4 and 0.7, stretching a little on both the sides. It could go to 0.8, it could go to 0.3, it depends upon the specific requirements. These will be my designs. Omega n, I cannot even give you numerical values, please, because really it depends upon the system hardware, it depends upon the system configuration. The range of omega n cannot be given, it can be as low as 1, it can be as high as 1000. So, you see that the range cannot be given, because it really depends upon the system hardware. So, that is why the value of zeta I am specifying to you, it is between the range between 0.4 and 0.7. And if I translate my requirements, you see characteristic equation of the system is s square plus 2 zeta omega n s plus omega n squared equal to 0. The two roots are s12 minus zeta omega n plus minus j omega n 1 minus zeta squared under the root. You will recall that these are the points corresponding to the roots. This was the omega n circle. This is your omega n magnitude, and this is minus zeta omega n, and this is a zeta curve. This is a zeta curve. Can you tell me what should be the region in the S plane for the closed loop poles for the requirements on the omega n and the zeta value we have specified? Come on, help me. First of all, there has to be some minimum value of omega n, because after all otherwise the rise time may become too large, and that minimum value of omega n, let me assume, is guided by this particular circle of radius omega n1, a minimum value of omega n, it is an omega n circle. A maximum value of omega n as dictated by the hardware and noise considerations. Let me say that this is omega n2, the numerical values I have not given you. Let us say that the value of zeta I take, this corresponds to zeta equal to 0.4. It means I will take this angle as cos inverse 0.4. I will take this as the value of zeta equal to 0.7, cos inverse 0.7. It means, please see, the complex root has to lie in this particular region and a corresponding point will lie in the lower region. So, you see that I have now given you the regions in the S plane. In a general application, the closed loop poles of the system are supposed to lie in this particular region in the state space. There will be 2 poles only, and the 2 poles preferably should lie in this region. These red curves guided by the considerations of the natural frequency, and the green curves guided by the considerations of damping. Okay? I hope this is okay, please. Right then. So far you see the discussion has been limited to a standard second order system, Ys by Rs equal to omega n squared over s squared plus 2 zeta omega n s plus omega n squared. Now, please help me when I take up the variations from the standards. After all, my actual system may not belong to this category. It may have more than 2 poles, it may have zeros also. So, how do I handle those situations is my next point, you see. Those situations can be handled this way. Let me assume that the system has a 0. Can you help me a situation? You already know the situation, please. I can assure you on the basis of the tutorial problems we have considered. Can you help me with this situation that there will be a 0 here and there will be 2 poles in the poles, closed loop poles of the system. This type of situation, have you ever come across this type of situations in the numericals you have handled? Yes, please see that. Intentionally, if you are introducing a PD control in the system, what will be the closed loop transfer function of the system? If you apply a PD control on a second order system, your transfer function is going to look like this. So, it means now in this particular case it has got 2 poles and a 0, and I really do not know how the system will behave when this particular 0 is also available or is either because of the system hardware or you have introduced because of your controller, whatever may be the reasons. But this 0 is now available, and hence I want to study the effect of this 0 on the transient response. Help me. I think you won't mind if I change the gain of the system by a factor 1 by z. That is, I multiply this by 1 by z. Why do I do it? Please see, I am doing it only because of this consideration that the steady state value of y should be equal to 1. So, that my comparison is with respect to 1, that is all. It is after all a gain. I can add any amount of gain in the system through amplifiers. 1 by z is not affecting my dynamics, I am studying the effect on the dynamics. So, you can see that if s tends to 0, the value of y will go to 1, which is the steady state value for a step input. You calculate the value of y for step input, which will turn out to be equal to 1. So, there is no other consideration other than this, that the transient response I want to study with respect to a steady state value of unity, and therefore, I have multiplied it by a gain of 1 by z. Okay. So, if this is the situation, then Ys by Rs becomes equal to omega n squared by z, s plus z divided by s squared plus 2 zeta omega n s plus omega n square. You won't mind if I write this as Ys equal to omega n squared over s squared plus 2 zeta omega n s plus omega n squared plus 1 by z s omega n squared over s squared plus 2 zeta omega n s plus omega n squared. Please look at this, hopefully it is right. Look at this equation, Rs of course on both sides. Why did I manage this way? Why did I manipulate the equation this way? I think some of you might have noted this. As far as this component of the response is concerned, it is your standard second order system response. And how about this component? This is a scale factor 1 by z, otherwise this component is the derivative of the standard second order response, because an s factor is coming. Okay. Normalized by this particular factor, our scale factor of 1 by z is there. So, it means what type of transient response do I expect, please? The transient response I expect is the following. This was your standard second order system, and the transient response because of the derivative component added to it is expected to look like this. Just add a derivative component to this. Initially the derivative is large because the slope is large, then the derivative is small because the slopes are small, and hence the effect of the derivative will be very large in the initial portion of the response and not in the later portion, okay, because the derivatives are large in the initial portion of the curve. So, the curve has been lifted up, you see, as far as the initial response is concerned because of the presence of 0. Okay. However, see the scale factor, 1 by z is the scale factor. Look at this, this was your the region which you said that mostly your closed loop poles will lie in this region. This is what we have said, mostly the closed loop poles lie in this region. So, it means as far as the decay of response is concerned, the decay of response is guided by zeta omega n, because zeta omega n is the real portion of the complex conjugate poles, and the response decay is guided by e to the power of minus zeta omega n t. You please note that the decay of the response is guided by e to the power of minus zeta omega n t, the other term is a sinusoidal term. So, the decay of the response is guided by the real part of these particular poles, and now in addition to this there is a 0. So, 0 is scale factor of the 0 is 1 by z. Please see, if z is equal to 0, that is if a 0 lies close to the origin, in that particular case the effect on the response is very large. But if z is equal to infinity, that is your 0 lies deep further into the left half plane, in that particular case the effect on the response is negligibly small. So, you see that relative position, yes please.
So, is it necessary that the 0 lie in the left half plane only?
Yes, this is another point, I will answer this point, okay. In my discussion I will keep this point also. You see that, first let me complete this and then go to his point. You see, assuming that the 0 is in the left half plane, in that particular case you find that the 0 deep into the left half plane has a lower effect on the system, and the 0 close to the imaginary axis has larger effect on the system. The guideline which you can by extensive simulation you can verify is this, that relative to this position of the complex conjugate poles, please note this is a very important statement useful in design, relative to this particular position, if the 0 is roughly 5 times away, in that particular case this is the region I have given you, the region of 0. The 0 naturally will be on the real axis if it is a real 0, I am considering only one 0, you see. If the 0 is roughly 5 times away, in that particular case its effect on the transient response can be considered negligible, okay. If that is the case, what is big thing we have achieved out of it? What I want to say is this, that all the performance measures of rise time, settling time, peak overshoot and all others, the peak time, they with respect to zeta and omega n, with respect to only denominator of this transfer function can be used for a system with a 0, provided the 0 lies in this particular region and not in this region. So, you can really assume as if 0 is not present, and in your design exercise you can go ahead with the same relationships we have derived, standard correlations which we have derived for a standard second order system will become applicable here when the 0 lies in this particular range. Okay, this is very important because you are going to use this information in your design. Suppose it does not. After all, a PD controller cannot be designed only because of this consideration, okay. So, if it does not, please see, the only thing we normally do is this, that you design your system and test it by simulation whether it satisfies your requirement or not. And one more thing you take care of is that suppose the design requires a value of zeta equal to 0.4, which corresponds to an overshoot of 25%. So, what you do is you design for a value of 0.5, so that you know that the 0 will will push the pronounced peak, and if you have designed for 0.5, which is let us say 16.3%, after all the deterioration because of 0 may take it towards 25%, which may turn out to be acceptable to you. However, the final value will have to be confirmed using simulation. So, you see that as far as the design cycle is concerned, you will look at these 2 points, either your 0 satisfies this requirement, or if 0 does not satisfy your requirement, re-enter the design cycle and take a value of zeta, so that it accounts for this effect of the 0. The pronounced peak is taken account of in deciding the value of zeta for which you are making a design. Instead of 0.4, I may make a design for 0.5 and see that, well, the final peak overshoot, which whatever comes may be acceptable to me. If the simulation does not give you acceptable value, you have to re-enter the cycle, this particular system. Okay. His question, please. His question is this, that is it necessarily required that a 0 is always in the left half plane? Please see this point. It is not necessarily required, because a 0 in the right half plane does not affect the stability of the system. But let me make a comment that in most of the physical situations, a 0 in the right half plane does not occur, but for the systems which have dead time. You see, a dead time is modeled as e to the power of minus s tau d. A good approximation of dead time is 1 minus s tau d by 2 divided by 1 plus s tau d by 2. This is a good approximation of dead time. So, you see that, and this dead time is very common in process control applications. Mostly process control applications are equipped with definitely give you the dead time value, and hence though 0 is not explicitly visible in dead time, but its effect is equivalent to a 0 in the right half plane, because this is closely modeled by this, and hence a 0 over here. Now, you see that if a 0 comes over here, what will happen? It means the peak overshoot or the derivative, instead of getting added up, it actually gets subtracted. So, what is the response you expect? Help me. The response you get if there is a 0 in the right half plane. This is the situation. If there is a 0 in the right half plane, I may give you a typical response like this. Initially, the peak overshoot will go down. The curve may not be nice, you see, but qualitative explanation should be taken, that the derivative scaled by the factor 1 by z will be subtracted from here, and therefore, the overshoot will not be there, but see the effect. The great effect will be that the response will become very sluggish. So, e to the power of minus s tau d is a very poor effect on the system. It makes the response very sluggish. And as far as peak overshoot is concerned, the peak overshoot may also be affected because of this, but the primary effect is this, that the response becomes sluggish. So, his question, a very important question for you is that the 0 in the right half plane is allowed as far as stability considerations are concerned, and the 0 comes up quite often in process control applications because of the dead time prevalent in the hardware. Okay. Okay, let me go to the next situation. The next situation, Ys by Rs, I say that, well, I have taken a second order model, a model which will never occur in a real life situation. Real life situation normally will consist of higher order models. Please see. So, let me exemplify it by including one more pole into the system, and then I will extend the logic to higher order systems, maybe 5th order, 10th order, or any order system. You see, do not limit your considerations to a standard second order system. As I said, standard second order system is an important design tool with us. This is a system. Tell me please, just normalize it for me, so that the response is taken with respect to a steady state value of 1. Help me please. What should I do? I want normalization of this particular transfer function. So, some constant here and there, so that the steady state response turns out to be 1 multiplied by p. Please see, this is the normalization I have got. Now, look at the effect of this. Looking at the effect of this, I find that there will be two modes in the system. One mode is e to the power of minus pt. Of course, the residue is going to dictate the magnitude of this particular mode. The other mode is e to the power of minus zeta omega nt. Again, the residue is going to dictate the magnitude of this particular mode. So, the total response of the third order system is based on these factors. One, the two modes now naturally will depend upon the relative location in the S plane. You can see that if a pole is deep into the left half plane, it decays faster. So, you see that if there is a pole towards infinity, its presence is not going to affect the transient performance of the system, because it will almost instantaneously decay. But if it is close to the j omega axis, or if it is close to these poles of interest to you, in that particular case its presence is going to affect the transient performance, because its decay is going to be comparable to the decay of e to the power of minus zeta omega nt. Another factor, of course, the magnitude of the decay is guided by the residues. Now again, without going to the quantitative aspects of the effect of this particular pole, let me generalize it to any system, a higher order system, a 10th order system for example. I say that let us, for a 10th order system or an nth order system in general, let me say that the design has given you this situation of poles and zeros. This is the design. There are two poles in this region depending upon the specifications you have imposed, and all other poles lie in this region, whether real poles or complex conjugate poles. All other poles lie in this region, and this particular region is about, or at least more than 5 times the real part of the complex conjugate poles. Okay, at least 5 times. In that particular case, you may take more than one poles. You can say that in this particular case the poles are insignificant, and hence as far as the study of transient behavior of the system is concerned, it can be neglected, and your transient behavior is primarily guided by these two poles, and hence the design can take care only zeta and omega n. Please see that if you are using the word zeta and omega n for a system, these terms become meaningless unless the system is a second order system. I hope you agree with my point. The terms zeta and omega n are meaningless unless the system is a second order system. So, if you are using the terms zeta and omega n for a higher order system, it means it is your responsibility to ensure that all the other poles other than the two poles given over here are giving insignificant contribution to the transient response of the system. This I will refer to as the dominance condition. So, it is your responsibility to see that the dominance condition is satisfied. Okay. So, unless the dominance condition is satisfied, you see, it does not mean that you cannot enter into the design cycle in that case. In that case, the only thing I can say that, well, you design for some zeta and omega n, check by simulation whether your design is acceptable to you or not. If not, well, it is a trial and error process. Go enter into the trial and error process and see to it that your finally simulation confirms your design requirements. Okay. One point very interesting, as I said that today you may not realize it, but all the design exercise is going to use what I am saying today. One important point is the following. You see that these are the poles, maybe the idea comes from you. These are the two poles, and there is another pole. The dominance condition is not satisfied. Very poor situation as far as dominance condition is concerned. I do not say that the response is poor, but as far as the dominance condition is concerned, it is a very poor situation, is not it? So, these are the complex. You can definitely for this particular system, if you say that the performance of this system is given by zeta and omega n, where zeta and omega n are given by these numerical values, I think you are making a very wrong statement. Okay? if zeta and omega n are given by these numerical values and you say that the response is guided by zeta and omega n, very wrong statement you are making. Tell me, in this particular case, can anyone generate some idea how to go for the design? How to go for the design? Very interesting point. I think yes.
The first order term would dominate in this case.
First order will no, in this particular case, if zeta omega n is equal to, let us say, minus phi, first order term will dominate in this case, you said, isn't it? Well, in that particular case, you see that either these should become insignificant. If these two poles become insignificant, then I can say that, well, my response is guided by this first order term. But suppose that these two terms do not, this first order term does not dominate, this gap is not large enough to say that the response is guided by the first order factor. So, neither by the first order nor by the second order your response can be represented. It is the full third order, and hence a full third order system response will have to be evaluated. And you want to design this particular system for some peak overshoot and omega n. You see, the user has given you some peak overshoot and settling time. The peak overshoot and settling time can be translated into zeta and omega n. Somehow, if you can, I can give you a hint, please see. Well, I think the hint may give the answer to me. If somehow you take off this pole, in that particular case the situation will be a happy situation. If somehow you take off this pole.
So, splitting the function into two isolated parts,
Adding a 0.
fractionating it, the function.
Alok, did you say adding a 0?
Yes, sir.
Yes, that is the answer, please. Just see that a 0 in the earlier discussion was a culprit, was creating problem, was giving you pronounced peak. But after all, a 0 you can introduce through a PD controller. So, why do not you design a PD controller and put a 0 here? Please see that if a pole, you see, if you put a 0 exactly on this, the dynamics gets completely cancelled. It means the residue at that particular pole becomes 0. Putting a 0 on the pole means the residue becomes equal to 0, and hence the effect of that particular pole has been removed. But even if the 0 is close to the pole, in that particular case, the contribution of this particular pole on the transient response of the system will be small, and therefore you can say that the dominance condition is satisfied, and you can say that the response of the system, third order system with a 0, is dictated by these two complex conjugate poles. And this is one of the design methods which we normally carry out. This is pole 0 cancellation method, in which a 0 is placed near a pole by design, so that the effect of this particular pole can be minimized. The effect is coming, you can just check, because of the effect on the residue of the system. The residue of the system gets changed in the process. Okay. Well, the target was completing the discussion today, but I see the time, let me not start with the steady state error. So, I think tomorrow I am going to complete the discussion on the subject with the discussion on steady state errors, one point, and second, a complete design example. This is left, and I am going to complete this tomorrow. Thank you.